Drinks.
All right, so everybody got everything working for today with your virtual machine and box?
It's got to recompile.
It was due 20 minutes ago.
Like I said, give me 2 minutes.
All right, so today we are moving forward towards how do we start considering C, programming language C, in the context of what we're doing here. Remind me, what is it? Actually, let me get this open so we can reference back to it. Remind me, what is a stack?
It's a data structure that
It's a FIFO data structure.
Yeah. Good job.
All right, first in, first out, data structure. When will we use these?
Want to remember where we were before?
Okay, so in the context of operating systems, I guess operating systems is a good example, and that's kind of where we're going here. Is typically when I ask that question, when do we use these? We start thinking about, the learning about the data structure itself from like the 300 class, and Towers of Hanoi, and remember we also did the shunting guard. We did shunting guard, right, for
I think that was 325.
reverse Polish. No, it's not. We do it in 300. Reverse Polish notation, kind of the upgraded version of process expression. Remember that when we have queues and stacks and it can support parentheses. I'm almost positive we did it in your 300.
I don't remember it.
Okay, well, whatever. It uses stacks and queues, or if you've ever used a reverse Polish calculator, HP usually makes, all of HP's calculators are that way. If you wanted to add two numbers together, like 2 and 3, you would take 2, push it onto the stack, 3, pushing on the stack. Then you'd say plus, and that would consume the top 2 elements of the stack, apply the 2 to it, apply the plus to it, pushing the result of 5 back onto the stack. So everything operates off of a stack. So the way that would work is we would push 2 onto the stack, then we would push 3 onto the stack, then we would issue the plus command, which would then fire a pop from the stack, apply plus to it, plus 2, plus 3, giving us a 5, pushing the 5 back onto the top of the stack. All right, so we often use the stacks to remember the most recent value, for example, or most recent values. As we think about this in terms of operating systems, stacks, as well as programming languages, when we start kind of merging those two things together, usually the way a function is implemented at the software level or the compiler level is let's say you have a function that takes 3 parameters, you would push those 3 parameters onto the stack so that the assembly language, the compiled code for your function, when you compile a C function, Java function, whatever, that's turning a high-level language into a low-level language like assembly. That assembly code that lives inside of the procedure or function, it needs a way of referencing its parameters, the parameters that were passed in. It will find those at the top of the stack. That's how that works. All right, so and we'll see here. I assume that it's going to show us some C examples with stack stuff. I think I remember seeing that when I was flipping through. Okay, so that's what a stack is. Now, because we're going to be because we want to write a majority of our operating system in C and not in assembly, we're going to have to provide for ourselves a stack data structure that allows us. So we think about stack data structures in general terms as a way we might solve generic problems, but maybe we put the capital T before this guy. And for an operating system, we must have the stack. There is the stack that exists that governs the whole operating system, that will use the stack for doing various things. In fact, low-level languages like assembler, i86 assembler or whatever, they have a special register specifically for holding the pointer to the top of the stack. It's called the stack pointer. Okay? So this idea of trusting that we have a stack to work with is a requisite for modern operating systems. And it's not something we just invented 5 minutes ago. It's been around for a long time with operating systems. Okay? So we're going to be reliant on this idea of a stack, and that is how we kind of can make the jump over to C development instead of having to do everything reliant on C functions and procedures rather than having to do everything in assembly. Go ahead.
At this OS level, are we kind of considering stack memory versus heap memory, or is that more
Not yet.
C specific?
Let's say neither. So the official answer to your question is not yet. Programming languages themselves will use a stack and a heap. Operating systems, traditionally modern ones, will use both a stack and a heap as well. And we'll see this as we go on, that these two different tools serve a similar process in that it's a place to put stuff. But we rely on the nature of how a stack works. A stack is absolutely required for an operating system where I think we could get away, well, a stack is absolutely required for an operating system that we want to be able to conveniently write in a high-level language. I think we can get away without a heap. You give up some abilities, or potentially give up some abilities. Let me think through that a little more, but I think that's at least mostly true. Okay, so let's. Oh, where am I? Oh, stop logging me out. Is there a button somewhere I can click on that says "Don't log"?
It's power. It's the power settings.
Where?
So go to settings.
Super Ninja.
And then power towards the bottom over there. That's what's causing the time. So yeah, just turn power saving off.
Turn power saving never. Aha. Okay. So we are moving towards, so we already have our basic operating system running that we ran last time. We're emulating x86. So kind of our goal today is to automate most of what we did for today by hand, with the idea that we are going to be making changes to our operating system, adding features to it, and maybe we don't want to have to by hand recreate the ELF kernel and the ISO and all those individual commands every single time. Does that make sense? We just kind of have a command that we can just run and say, test the new OS. Knowing that all that stuff that we just did by hand for this week is happening. It's a requirement. It has to happen. All the linking and the compiling and the NASMs and the NASM doesn't have to happen except unless you make a change to the low-level stuff, but this is beneficial for us as we start making changes. Okay. So we need to set up a stack in our operating system. So this is the stack that I was just referencing, right? So not a stack, the stack. So not to be, and I just referenced the stack pointer that we have. So in assembly, NASM, we have a stack pointer right here. So EAX is like the AX register, EBX is the BX register, ESP is the stack pointer. That's what SP stands for there. All right, so that's going to be a place that lives on the CPU. It's a piece of memory really fast that remembers where the top of the stack is. Okay? So we're going to have to create this stack in our assembly code initially. All right, so we're going to give ourselves a size of our stack. I believe it reads it in reverse. So we start farther in memory and work backwards. We'll see that here shortly. So we are going to have this global variable here called kernel stack size. And we're going to set this guy equal to 4096. And that is bytes. So that is 4 kilobytes. That's how big our stack will be in our simple little operating system. Maybe a little bit small if we're dealing with a little bit more powerful OS, but good enough. You know, we can put a lot of stuff on there for us. Okay. Now we have a new section that we're introducing here, section.bss. This is a section for unused memory, but that's the wrong word. I'm looking for reserved might actually, well, reserved is more accurate. Unreserved is more accurate than unused. But we haven't actually requested the memory yet. It'll pop into my head soon. But for the moment, let me open up our oh, by the way, you can get Visual Studio Code for Linux if you want it.
Can you get 2019?
I don't know. I mean, this is their text editor.
Different program.
Yeah.
VS Code is done.
Yeah, so you would want to go and get the Debian package for VS Code. If you go to the website, you can get the Debian package. Then you can use git install / wherever the Debian package is. And that'll install it and any prerequisites for it. And then the code itself to launch it is just code. That's the executable. And once it pops up the first time, you'll be able to right click and say, yeah. So here, let me show that to you real quick. Yeah, so I downloaded this from Visual Studio Code's website. So you'll say sudo apt install ninja install / make sure you're in the same directory, or at least you give it the full path where it can find that file. It's going to ask me for my password for sudo, and it's going to go and say I already have it installed. That's why it's cool with it right now. So it's saying code is already already the newest version, blah, blah, blah. But for you, it'll ask you, do you want to install such and such prerequisite software? You have to type in Y and press enter. Then it'll download anything it needs to make it work. After that, you just type in code and press enter, and that'll launch Visual Studio Code like this, giving you this guy over here on the left. And from that point, you can just right click on this and say add to favorites. And then it'll be over here in your quick launch bar on the left. This will give you a friendlier text editor than we've been using up to this point. Make sense?
You mean Nano is super?
No, I'm with you. I'm with you. Just
Even highlights your code and everything.
I do want to encourage you to use command line tools as much as possible, but I also want I want us to make sure we're focusing in on the assembly code and the low-level code, and focus on that rather than weird text editor thingies. But everybody up to this point, coming for this last week, you use command line tools and stuff to do stuff, so you've had that experience of this isn't the friendliest thing in the world, but maybe you got a little bit more used to it than you thought you would have, something like that. All right, so let me go ahead. What happened? I'll just open the individual file. I was trying to give myself the whole folder, but that's okay. So where is my... So here's my loader file. All right. So we're going to add some new things to our global for our loader. So I'll go back in here. Oh, I'm in Linux already. So I'm going to grab my kernel stack variable here, and I'll throw that here at the top of my loader. This is just a global variable, kernel stack size, all caps. Usually when you see something in all caps, that's telling you it's a global variable, part of the what's called the macro system. It's going to be equal to 4096. I'm too used to switching between apps on the Mac, so I keep using the same. All right, so I'm actually just going to copy this whole thing so I don't drive myself insane. Before I drive myself insane. So we're adding another section here. So notice down here we have a section called text. I'm now going to give myself a section called BSS. Now you've seen in here, we saw it last time, this thing called a line 4. So what this is saying is we're going to, so it's a line 4 bytes. So if we think of this like an array, every single time we take a step, we're taking a 4 byte step. As we walk through memory. So by aligning it by 4, what it'll do is anytime we have something in a bucket of memory that doesn't fill up the entire 4 bytes, it will pad it with zeros for us. That makes sense? Guaranteeing that when we take our next step, we're starting with the next element in memory and not working with the last half of the previous value, or more reasonably, when we start working with our next value, we're not using the first 7 bits of the previous value as the first part of our next value. It gives us discrete 4-byte buckets that our data is to be stored in. So we can't fill it with more than 32 bits in a single place, or 4 bytes. But if we do put a smaller value than 4 bytes in a bucket, it pads it out with zeros to guarantee that our next value has a fresh starting point. Think of it like a container size. You don't have to fill your containers, but we do have discrete container sizes. That make sense? All right, so this allows us to line these things up. So if you think about yourself, you like have a robotic arm that's moving from value to value to value, we can program that arm to move from bucket 0 to byte 4 to byte 8. So on and so forth, knowing that we're at the beginning of the next chunk of data, even if the previous container was half empty. Okay? So that's what this align thing is for. We don't have to do any of the magic. We're just saying, give me bucket sizes of 4 bytes and make sure you allow me to trust that that's the case. Well, probably not wasting a lot of space, because the most space you'd waste is 31 bits. But the trade-off is, so you gain efficiency, translating into quite a bit. You gain speed efficiency, possibly memory inefficiency, but the trade-off is probably okay given how big our RAM is, right? And you also gain predictability. And what you're trading off is, at most, if we think about this in terms of paging memory management in the operating systems class, worst case 31 bits of internal fragmentation, which in our world 31 bits not that big of a deal. Even if you add it up over 500,000 times, still not that big of a deal, because we don't care about the computer's feelings or any of that stuff. If we could be wasteful with memory and it not really matter, then we would make a different decision. Now, historically, this kind of goes along with your question, maybe we would choose to align at 1. Do 1 byte jumps. So the most we're ever wasting is 7 bits. Something like that. But we typically think of our modern operating systems as being 32 or even 64-bit operating systems. So we give ourselves those bucket sizes because we're less concerned about wasting memory in that small amount, relatively speaking. Keeps getting onto FalconNet. No, doesn't matter. Okay, the sharing the internet thing is what you have to do for the Raspberry Pi if you want to connect to it over the Ethernet port. So I actually could just turn it off. In fact, let me just turn that off.
What do you think of doing it that way? Is it?
So I don't need to connect an external screen or.
No, I mean, do you think it's beneficial for students to use that way, or should they just use VMs?
Well, I would always use a VM.
Okay.
Yeah. If it were me.
Mhm.
This is more of the hack. You set up internet sharing over your LAN, and then when you plug your Raspberry Pi into it with an Ethernet, it'll be handed a non-routable IP address, but an IP address you can get to.
Okay.
And then you could SSH into your Raspberry Pi and power your Raspberry Pi off of USB, not have to hook up an external monitor or keyboard to it. And then you can even get a VNC server set up and be able to create a whole a headless VNC windowing system on your Raspberry Pi, and that can be your virtual machine just sitting right next to you, powered off USB and hooked in over Ethernet. It's an option, but if you have the horsepower, run a virtual machine and move on with life. Would be my 2 cents. Okay, so we have our BSS section, and we're saying we want to go ahead and have this aligned by 4. We want something called a kernel stack. All right, and this is going to go ahead and reserve some memory. How much memory? Kernel stack size memory. So this is going to grab us 4096 bytes, 4 kilobytes of memory inside of the BSS section, which will be reminded here in a few minutes, but we actually do reference this in our linker from last time. Remember last time we had our linker, the LD command, right? Was that our inside joke that you guys were joking about earlier?
I named
Yeah,
ID instead of LD.
file.
Oh.
Recompile.
Gotcha. All right. So LD is our linker. Now that we've gone through the process of getting stuff working, what do you think? What can you tell me a linker is? If you were to define a linker, what would you say? Kind of an important piece to. I'll just do it on the slide right before this. Well, do I ever have compiler in here? I don't. So let's go ahead and remind me, what's a compiler?
Program which
Okay. Well,
Not quite, but
ish. Yeah. So converts high level code to low level code. All right. That's what a compiler does. Ideally, we want to be working in C. That's the purpose of today's class. That's the purpose of chapter 3. While this low-level NASM stuff is fun and cool and makes us feel powerful, if our whole life lived there, we might get upset, right? But what's important here is we're seeing what's actually happening under the hood. That's what we really want to see in this class is how does Windows or Linux or the Mac OS, how does it actually run on this computer? We have to make all these individual pieces talk to each other. What's that process like? If we put ourselves in the initial inventor's mindset and we were trying to magically make all this hardware, launch something that we invented and turn it into Cafe Babe from our first little project or something like that, which is useless but real, right? We saw a real value show up in a hardware register from something that we invented. Not something that started at DOS or started at Windows or started in Mac OS or Linux. It was something that we created. We installed our stupid operating system off that ISO. And we can appreciate that initial stuff here was part of it, right? So we had our global variables. We didn't have a BSS section. We just didn't use it. We had our text session, or section rather. And then what did we do upon loading? We moved into EAX a value. This is the executable of our operating system. And then what did we do? We waited for eternity without giving you a prompt and without trying to read input. So we just sat here and just stared. What was the Chuck Norris joke? He waits. What's the question? There's some, yeah, Chuck Norris doesn't do something or something. He waits. It's funny when you hear the whole thing.
He doesn't age. Is that what it is?
I don't think so.
There,
Okay, so that's kind of what's going on here, but we can kind of understand that our ultimate goal is we'd like to use higher level languages as often as we can. Correct? We need to get ourselves into the position where we can use our higher level languages, and we know there's a necessity for that low level stuff. But the quicker we can transition from that, the better. So a compiler, we know, converts high level code to low level code. Now, we randomly used this linker last time, LD, right? What does a linker do? Here, I'm going to give you a little hint here. For us, compiler made a bunch of object files, .o files. That's what our compiler did. It created object files for us, which is low-level code. What does a linker do?
Like link the object files together into an executable.
Okay. Yeah, I was going to yell and say you can't yet necessarily use the word link when you're defining linker, but what does it do? Well, ultimately, when we run a program on our computer, we need an executable. Whatever that means for our system, right? Windows, it's a .exe file or a .bat or a .com file if you go back to the old DOS days. We need some kind of file that is executable on that operating system. So in this case, we need to generate an executable file. What does a linker do? It combines all of the object, that is the .o files, into a single executable file. And if you remember, when we looked at our linker file last time, what was it really doing? It was grabbing all the different sections from all those different object files. We're effectively here looking at an object file. That make sense? That's what we're looking at. We're writing the output of a compiler. Okay? Compilers translate from a high-level language to a low-level language. We're looking at a low-level language here. All right? Now, a linker is going to take all of those compiled files and now turn it into an executable that we can run. Okay? And if we go and look at our configuration file for our linker, here's our link.ld file. Okay, so notice it's saying, okay, our entry point for our executable is going to be whatever's in loader, right? And what do we see in loader? This is what our operating system does. When our executable starts, it should go there. All programs begin and end with main. This is equivalent of main for our operating system. Okay? And then we start collecting our sections. All right, we're saying where should this guy be loaded, and this is a directive that kind of from grub. The grub bootloader tells us this is where I'm going to start looking for your OS. So if we want this guy to automatically launch for us, we got to make sure we put him in the special place. Okay, but then what do we start doing? we start collecting our text sections, collecting our read-only data sections, collecting our data sections, collecting our BSS sections. So from all of our object files, we're bringing all those things together into this single executable and then telling it to go to loader first to start. That make sense? Go ahead.
What was BSS again?
BSS is remember you and I were trying to come up with what the, here, hold on. No, it's the unreserved memory.
Oh, okay, gotcha.
Data segments, yeah, here. Uninitialized data. Uninitialized is the word I was looking for.
Okay.
So this is like an area of unused memory.
So it's just like sectioning off that memory to be used.
It's the heap before the heap.
I see.
So it's this is where we unorganize them. This is where we store all our extra stuff in an unorganized way,
All right.
but in a blocked off place. All right.
It's like how you pile your dirty clothes in the closet.
Ah.
It's a nice big mess, but it's kind of out of the way.
Organized chaos.
Okay, so we see what the linker is doing here is it's just gathering all of our assembly code together into a single place and telling us where to start. Make sense? So Jack said it effectively links our files, but it combines all of our files into a single executable that we can then run. Make sense? All right, so that's what was happening with the linking portion here. So let's get back here. So combines all the object.o files into a single executable file that we can actually run.
That was our ELF file.
That's what our ELF file ended up being. Yep.
That's the
Yeah.
Oh.
ELF stands for executable linkable file. I think that's what ELF stands for. Executable linkable file. Go ahead.
So could we just run the ELF file and it would put Cafe Babe in that register?
That's a good question.
I mean, it wouldn't be on a separate machine.
Um,
related, but
Now I understand.
I don't think we can execute it because we linked it for, well, let's try it.
yeah.
Doesn't give me an error.
We have no way of looking at it.
Yeah.
Yeah.
I mean, it's just an infinite loop.
Now I understand what was going on when I was messing with all the files on my Wii when I was younger. Messing with the .elf files and wondering how the heck to open them.
They put an ELF map.
Yeah.
On my shoulder?
So there's our program, our executable running.
Okay.
And if we had a way of looking at the registers, we would see it.
Okay.
But we don't. That's why we emulated the machine so we can look at it.
And this is, I guess, it's kind of a side question, but with our executable file that we made, does it just put Cafe Babe in there once and then loops waiting, or does it put Cafe Babe in that register continually?
Once and then waits.
Okay.
Yeah. Okay. So we added a BSS section here, and in our BSS section, where did I put it? We're again aligning by 4. We have our kernel stack. So this is a label that we're putting in here. So think of that like a function. All right, so kernel stack, we happen to name it kernel stack, but somebody has to call upon this guy to get kernel stack to do anything. It's not some sort of special built-in thing. I could have named this elephant if I wanted to. But whenever I want to use the stack, I need to make sure I call upon elephant at that point in time. This is human naming here. We just, kernel is operating system, stack is the stack of the operating system. Go ahead.
Remind me what resb is again. That's just reserving.
This reserves bytes
Reserves bytes.
of size kernel stack size.
Okay.
And that is 4096. This guy is actually a not a regular low-level instruction. He is a pseudo instruction. Yeah, so all these guys, this is declaring uninitialized data. So These are designed to be used in the BSS section of a module. They declare uninitialized storage space. Each take a single operand, which is the number of bytes, words, double words, or whatever to reserve. NASM does not.
It literally says or whatever.
Or whatever, yeah. Well, it's going to be in terms of what you aligned.
Okay.
So NASM does not support specific. So these are various assemblers. Anything that has ASM at the end of it, usually that's a naming convention for an assembler. And what does an assembler do? So we've talked about compilers. Compilers turn high-level code into low-level code. What does assemblers do?
Low code to machine level.
Yeah, low-level code to machine code. That's the last swing to get Austin's answer from earlier. So an assembler converts low-level code to machine code. So at that very last part, this is where it actually becomes the zeros and ones. Yeah.
So is an object file, is it machine code then?
An object file would be low-level code.
Okay.
Yeah.
Isn't that what you get out of an assembler or like?
It's what you're going to get out of a linker. Let's see. No, we're running NASM. NASM produces object code, which would be machine code. Yes, that's machine code, not low-level code. So whenever we run NASM, which is an assembler, the output is machine code because that's what assemblers do. And so the output of NASM was a .o file, so that means that's machine code. So when we say linker, linker is going to combine all of the machine code into a single executable file instead of low-level code. Okay, so we reserved our stack space. So now inside of the BSS section, we have 4 kilobytes of initialized memory to work with. Okay, our text section has not changed. We are going to do something inside of loader here, though, in a minute, I would predict. Okay. All right, so now that we have that stuff inside of our loader, inside of our executable thing here, doesn't really matter where we put it in here, which line we put it in. Whatever. All right, so we are moving into the stack pointer. So this is a hardware register built for holding the pointer to our stack. What are we moving? We are moving the location of kernel stack, which is this label right here, wherever that ends up in memory, plus the kernel stack size. So this kernel stack here is like a base address. When we think about base addresses for arrays, so if you have a int array AR equals new int array 100, that's going to give us a memory address somewhere in memory, right? Bucket 3 of that array will be the base address plus 3 times the size of whatever that array is built to store. So wherever that array lives in memory is the base address, then we offset from it to get to our bucket. This is the base address of wherever kernel stack ends up being placed in memory. We're adding to it 4096 bytes. This puts us at the very end of the space that we have initialized for our stack. Make sense? So our stack actually works backwards. So if we think about draw a picture for stack. Call this the stack. We have a variable called, in assembly we're calling it a label. I'm going to reference it as a variable. It's ultimately that section, that label is going to have a place that it lives in memory. All right, and this is kernel underscore stack. So somewhere in memory, we're going to have a pointer that points to an actual place in uninitialized space in the BSS area of our computer's memory. And this is going to be effectively, we can think of this like an array for the moment. Then we're going to think of it like a stack. All right, so a whole bunch of boxes later. So, all right, so this is just copy all this. And then, of course, these would be green. Whatever, just deal. So this is bucket 0. This is bucket 1. This is bucket 4095, because we have 4096 4-byte buckets because our align size is 4. So when we say kernel stack and we're trying to set our stack pointer register equal to something, we're setting it equal to whatever kernel stack is, which is this base address. So if I want to think about base addresses here, this guy lives in memory somewhere. So maybe this is memory address 100. This would be 104, so on and so forth. This would be 4092. All right, so this is a place in memory. So kernel stack starts at memory address, by my example, memory address 100. We add to that 4096, the size of it. That's going to take us, actually this is 4192, sorry. So it's going to take us all the way to the end, past the last bucket. So that means our SP points to the top of the stack. So the top of our stack is the value at the very end of the stack. That's what's happening in this code right here. Move into our stack pointer, whatever address you found in kernel stack, wherever that got loaded into memory, and add to it your kernel stack size, which is 4096. And that will place the stack pointer pointing to what we are viewing as the end of the stack, but what in actuality is the beginning of the stack, the top of the stack. So our stack is kind of stored by human mentality backwards. So when we start pushing things onto the stack, those things are going to get shoved down this way. So I might initially push on a 5, and then I push on a 4. The 5 will go here, the 4 will go here, so on and so forth. Does that make sense? We push from that side.
And that's just like, so we know the end of the list, or list, or whatever.
Well, it's because we reserve stack space, and now we've comfortably given ourselves space out here where we can put other crap. We've just said, look, here's our constraint. You start at the end. You can start filling stuff. When you get to the base address of this, no more. Stack Overflow exception, as Java would say. Right? You filled it with too much stuff.
Alright.
Go ahead.
So just to double check with the illustration, is the green the bucket number?
Yeah.
Okay.
I have a question. How about the red one? Like, how do you get the 4192?
Well, I know that there is 4196 bytes in here. This is bucket 0, bucket 1, bucket 41. Actually, this 41, this is not accurate. This is actually 1024. 1023, rather. Yeah, so there are 1024 total 4-byte buckets, equaling a total stack size of 4096 bytes.
Okay, how do you get the 1023? Like, I
So we have, here, I'm going to write it here. We have 4096 bytes of total stack space. Each space is 4 bytes, each, let's call it each bucket in the stack is 4 bytes. So we have 1024 buckets. That's what this is. Bucket 0 to bucket 1023.
So you just take 4096 divided by 4.
4096 total stack size divided by bucket size, which is our alignment. So divided by 4, we have 1024 buckets, which are, we're saying, I just magically invented that the base address was 100. All right, so we're saying if kernel stack started at 100, the beginning of the last bucket would be at 4192. So that's 192, 193, 194, 195. So for our last 4 bytes of our last bucket. That makes sense? And RSP is going to get set. This is our stack pointer. SP stands for stack pointer. That guy gets set to point to the very last bucket in our stack, and then we work forward. So we've said, look, this space reserved for our stack. Fill it, don't fill it. We don't care. Nothing else is going in here. But now we know that we can put other stuff after kernel stack space out here. Whatever that means for us, knowing that we're not going to mess with that with our stack. That makes sense? This is related to, see, you guys have not had 325? You have had 325. Computer organization architecture. There's something called Little Endian notation versus Big Endian notation. This has to do with whether or not you start at the high bits or the low bits. We talk about it in there. Just for this, just let's say this is the way it works. Okay? Huh? I teach that class. The reason it isn't, you probably haven't had it, is it fell out of the major.
I haven't seen that class.
Well, now it's back in the major.
Oh.
It's a very important class. Because as computer science majors, we should know how computers work. It seems like that's a thing. Go ahead.
I was just wondering if that's offered like next semester, because I'm on the old track still,
Yeah.
and I haven't had it, and it hasn't been available.
Yeah. Probably.
Okay.
I have a side thought. If you don't need the credit, but are interested in taking it type of thing. I mean,
I'll have
he has a
extra
YouTube channel.
credits.
I'm guessing
No,
you have
that's
your video up there.
Yeah. Yeah. Well, we'll figure it out. It's going to be offered soon, so it's if it's not next semester, it'll be the semester after. You graduate this semester, though, right?
I'm graduating in December.
Oh, okay. We'll figure it out. All right. So that's what's happening right here. We're setting our stack pointer equal to this, and we're setting EAX equal to Cafe Babe. Nothing else. So our OS got slightly more interesting, just slightly. All right. Well, it looks like there's .s and .ld file extensions for Visual Studio Code that might make our lives easier. I don't know. I'm not going to look at it. Okay. So that's what's happening here. Everybody cool with that so far? We've made a stack in our operating system. We've decided what that means. Okay? So here's calling C code from assembly. This is an example. So if I were to write this program in C, where I have sum of 3, taking 3 integer arguments, and then I'm just adding those together, whatever. What would this guy look like? Well, we would have a sum of 3 external label, and then we would push 3 elements onto the stack. So we push argument 3, argument 2, argument 1. So we push them in right to left order. So as we are executing our code, the presumption would be that at the top of the stack would be our first argument. The guy right underneath that is the second argument. The guy right underneath that is the third argument. But in order for that to be a truth, they have to be pushed onto the stack in reverse. I push arg3 on first, then I push down on top of that arg2, then I push down on top of that arg1. So now the top of the stack is arg1, the next element is arg2, the last element is arg3. So we have to stay consistent with that. If we want to rely on our command line, we want to rely on our parameters that are coming into our functions to be stored in left to right order on the stack, we have to push them on in right to left order. Make sense? Okay. Not really necessarily our problem here, okay? But that's how it's functioning. At least it's not our problem yet. All right, so.
I have a question. So would that be first in, last out instead of first in, first out?
First in. This is, yeah, we're dealing with.
Because I heard you mention about the FIFO thing, but then I still don't wonder how is that even work?
This is a LIFO queue.
Oh.
We should have written that. Did we not write that?
Oh, actually, we wrote FIFO.
Yeah, we wrote FIFO, but not.
Who said FIFO?
Josh.
Yeah. This is last in, first out. That's what a stack is.
Wow. Sometimes that all just.
The last thing that was in is the first thing that comes out. So the last thing we pushed onto the stack here was arg1. That'll be the first thing that comes off the stack when we start peeling them off. All right, so now they talk about, this is more of a standard of how we store things. The book is using something called packing structs with the idea, it's kind of a hack. So it allows us to think about the different components of a value in terms of its base address and things like that, knowing that after it's compiled, it's ultimately going to be 32 bits of stuff. So instead of using a single 32-bit unsigned integer, we can create a 8-bit unsigned integer that maybe is our index, a 24-bit unsigned integer, no, it's a
8 bits config, right?
so 816, so 16-bit address space. So 16 bits of address space here. So that would be a short. And then this is another 8 bits configuration bits. That's another char. So chars are 8-bit bytes, are 1 byte big. A short is 16 bits, 2 bytes. And a char, again, is 8 bits, 1 byte. So they create a struct here that holds a char, a short, a char. And if you add up 8 plus 16 plus 8, you will be left with 32 bits. And their cheat thing here is that a struct is like an object, but without functions or procedures. It's the fields. It's an object in terms of just its fields. We can think of the structs were the precursor to objects. That's what we used in C before we had objects in C++. So this guy is a collection of name value pairs. Dictionary in Python, it's like a struct. All right. So we happen to cheat off the idea that we know when this C code gets compiled, at the end of the day, it will be stored as 32 bits.
Okay.
8 plus 16 plus 8. So it allows us as programmers to visualize this in terms of the config, followed by the address, followed by the index. All right, so we'll see how they use this later, but that's what's happening there. It's a kind of a cheat.
So then, do we have to memorize how much each different type is?
Well, no, I mean, this is our decision in our programming language. I mean, we're choosing these values. But in terms of our example here, this is what it is. This is what we're using. This isn't this is how all operating systems work thing. This is, we're going to store 32 bits of stuff in our 32-bit operating system, and this is what these 32 bits mean. The first 8 bits mean this, the second 16 bits mean this, the last 8 bits mean this. However we're going to use those for right now. We're just giving them arbitrary labels as far as we're concerned right now.
Because otherwise we could, I mean, I guess the harder way, the non-cheat way is, I guess what you're saying is just having 132, I guess that's a long, right? Okay, no.
32 would be an int.
An int, okay. But we just have an int then and we just kind of concatenate the numbers together instead.
Yeah, with any padding.
Yes.
We'd be in charge of our own padding then.
Okay.
Yeah, so.
This way we don't have to do that.
And this is more object-oriented-ish.
Yeah.
Because remember, the whole reason we're looking at this stuff right now is because we would rather write C code than write assembler. Right?
Yeah.
And this is the whole purpose. This goes all the way back to CSC450. What's the purpose of a programming language? To allow us to solve problems in a way that's similar to how we solve problems in real life. This is all cool. It's awesome to sit here and think that, at the memory level, we're creating our stack. I'm not going to let anybody make any power tools for me. We're just going to build our own thing. I'm not going to run DOS anymore. We're going to run Cafe Babe. We're just going to get the whole department moved over to Cafe Babe here as the base OS. Okay, all this stuff is cool and we can appreciate it as computer scientists, but at the end of the day, we're still human, and we really want to wield at least C. We're going to complain about C. We're going to say C seems too difficult to use, or I have to write too much extra syntax, or memory is hard, or any other crybaby things we might do, okay? But the punchline is going to be that we're going to complain about C. If we're going to complain about C, what are we going to say about assembler? Let's drop and become history majors or English majors or one of those other useless majors. Actually, I was in a meeting with Dr. Cario this afternoon, and for those of you who don't, he's the provost guy, so he's like in charge of anything academics at the university, but he's a history prof. No, but it was actually fascinating what we're talking about. So this is at the chairs meeting. We're kind of talking about challenges we have as a university, as our clients are changing, the students are changing, and looking at, like if you've heard of Southern New Hampshire University, having all these online things, and they're growing faster like any other school, and how do we compete with that? One of their biggest majors is history.
Really?
Yeah, it was fascinating. But other schools have large majors in history. Harvard was one of them. I think Dartmouth was another one. And then another school that was similar to Southern New Hampshire, a school you've never heard of, or a nothing school. But it's fascinating.
Why?
I think the argument is that liberal arts aren't dead.
Okay.
Something along those lines. and what
That's
lesson
what
can we?
students are saying, or because I mean, students are choosing it.
Yeah, I don't know. Maybe it's time to completion or whatever. Yeah, I have no idea.
There are quite a few people that are interested in history, so
Yeah, well, there's a difference between being interested and being able to feed yourself.
that's fair. Yeah.
So, those are two very different approaches
You
to
want to
the,
turn what you're interested in something that you can use to feed yourself.
that would be my approach to life, but that's not always the case.
That's fair, I suppose.
It's like if you're a bad artist.
Yeah.
I have a friend who's
Might love
attempting
it.
that.
All right, so that's why we're creating this struct thing here is it makes life easier for us. This is how we think about things, and we're doing everything we can to be impressed by all these bits and bytes stuff, but start moving towards having things a lot easier for us to work with. All right, and they're talking about that it's possible. See, this packed attribute thing isn't part of the C standard. So we'll see in a little bit that we're going to turn off a whole bunch of built-in function stuff from C. But whatever. So this might not work in all C compilers, but it should work in GNU. GNU is a pretty forward-thinking compiler thingy. All right, so when we compile C code, a lot of flags to GCC need to be used. This is because the C code should not assume the presence of a standard library, especially not for our operating system where standard isn't even defined, right? Our operating system knows how to do nothing. Okay, so any of these libraries are things that we are not going to be able to support anyways because we don't really have anything, right? We have nothing. We have an empty stack and one value in a register. That's our entire OS. All right, so they're going to turn off all of these things. And then, so this is no standard library. I don't know, this is no standard something. No standard include. No built-in functions. No stack protector. No start files. No default libraries. And I'm guessing this is make it 32 bits. The big W's, this is with. So with all, with extra, with error. So turn on all warnings and treat warnings as errors.
Did you say what the F was in the previous code? Like F no built in?
Well, here I can tell you real quick. GCC dash H help grep for options starting with so things that have a dash F or any of these other things associated with it are automatically passed on to things that are using that compiler. So this no built-in, this is going to be something that we're going to be looking at make files here in a second, would be passed on to the make program. All right, so let me copy all of this first.
Just out of curiosity, how do you paste in
Paste in Vim.
Vim?
So no, you can
Yeah.
copy paste just fine, but you have to have it from a Firefox inside of the.
Well, if you're in there, just hit Shift Control V. We'll paste in there as long as you're in the
I
insert
don't
mode.
think you're gonna be able to paste in from outside of VirtualBox.
How was that? Wait, but it didn't paste. It took off the clipboard instead of pasting it correctly.
All right, so I'm going to create a file here. How are we doing on time? We okay on time? 3:30. Okay. So I'm going to create a new file here called a make file, and so we would call this one of our build tools. I'm going to just put it at this top level directory, so it's going to be called make file like this. And I'll go ahead and paste this stuff in here. And notice it already did a little color coding for me. All right, so we are going to have a file called main here in a second, kind of like all programs begin and end with main. In fact, let me quickly, I want to glance real quick, no extension, just make file with a capital M. Where did they make their kmain.c? All right, it looks like they want this stuff in kmain.c. So I'm going to save this kmain.c. I'll paste this function in there. Now, if you've looked at other C stuff, sometimes you prototype your functions up top and then you write them later on. I'll just leave it at the top so it's already prototyped. And we'll talk about that later. I don't want to get too much into C stuff for the moment. I'm kind of making a guess here as to what they want us to do, creating this kmain file. Then we're embedding some well, I'm guessing they're showing us what the assembly code is going to look like. Well, I'll leave it in there for a second because this is going to get weird. And then lastly, I'll give myself my struct. And this was a thing they were saying might not work. Let me just quickly see here what this guy does when I do GCC. That wasn't what I was expecting. Then kmain. Yeah, this isn't a well-formed C file. Do they tell us what they want their kmain to look like here? They should certainly act like it's already there. So we have our makefile, we're in the middle of writing. We already have our loader. We already have this whole structure that we worked with last time. So we've made a modification to our loader. We're in the middle of talking about makefile kmain.c. I think the idea here is that they're showing us the equivalent assembly code to what this guy will end up being. So I'm going to take out that stuff. That's showing us how the compiler or how the compile code would look after you run this. So we have our function called sum of 3, which is callable, but we're not actually calling it from anywhere. Then we have a struct that we're calling example here that could hold these things. Then we have this attribute pack thing, which they said might not work in all compilers, but I think it should work in ours. And do I have a kmain dot Yep, A dot out. Let me just make sure that that is what got created there. Yep. Okay. So that guy does compile. So that's what our K-main, I believe, is supposed to be. So K-main should look like this. It should be a sample function that we may or may not ever call. And then it should be our struct type that we haven't used yet, but we would use in preparation for all this. Because remember, this section is called build tools, so we're trying to automate our operating system as well as we possibly can. All right, so now I'm going to go back to my Makefile. All right, so my Makefile, it relies on two machine code files, two object object code files, loader and K-main. All right, so what a Makefile is, it's an automated way of doing a bunch of stuff. All right, so ultimately I have two low-level file or two machine code files, loader and K-main, and I want to turn them into an executable. Right? So who's going to compile this? GCC. So the C compiler we're going to use is called GCC. The C flags we're going to use is all of this crap that we just tested, right? The linker flags we're going to use is -t, link LD, then our L5386. We recognize that from last week. That was the thing we used along with the LD command. Those were our arguments to that. Our assembler is called NASM. Any flags we're going to send to our assembler is -f and elf. That's the type of executable linkable file we're creating. All right. So now we have a section called all. Should be producing something called kernel.elf. So this is where we're starting. Kernel.elf says for all of our objects, run the linker with our LD flags and all the objects, creating an output file called kernel.elf. Then to produce our os.iso file, given kernel.elf, we're going to copy kernel.elf into the correct place in our directory structure, just like we did by hand, right? Then we're going to do our gen ISO image, all this crap. So this is identical to what we already did by hand. But we've put it into this specially formatted file called a Makefile that works with an executable, a pre-installed software program called Make. Okay, so Make knows how to read a Makefile and does all of these steps for us automatically so that we don't have to manually do it again. Make sense? Go ahead.
This is a little bit off topic, but is the slash there just like it allows you to
Kick it down the line.
Yeah.
This allows it to be readable by us here.
That's
Yeah.
what I thought.
It was also exactly how it was in the book. But yeah, this guy says kick it down the line because this is the escape character in code.
Okay.
So kick it down the line, but don't break anything.
Because when I did before, I just did it all in one line. So thanks.
All right, so to get our os.iso, copy our kernel.elf file that's been built from up here into the correct location in this directory structure, then call a built-in program called gen ISO image with all those things. Then we have a directive called run. And in order for run to work, we have to have os.iso being completed. And what do we do with run? We call box, passing it our configuration file, our resource file for box. Same thing we did before, right? How do we get our object files? Well, we get our object files by compiling all of our C files. We use our C compiler, whatever CC pointed to, which for us was GCC, along with the C flags, giving it our input file, whatever the .c was, -o, creating an object file. This is the shorthand for this guy, whatever the thing was called .o. So these are all maker. This is a make file syntax. So think of this like an XML or an HTML. This is like a specialized the way you speak to the Make program, the protocol for Make.
It's a little bit funky.
All right. So how do we create .o files from an S file? Well, we use our assembler along with our assembler flags, ultimately creating our output file. Then we also have a directive called clean, which removes everything from the current directory that ends in a .o, also kernel.elf, also os.iso. That cleans everything up.
So basically, it deletes all the files that it made after it's finished packaging them.
Yep. All right, so I'll save that guy. I hit Command S on a Mac, so for you it would be Control S.
Yeah, because I've just been writing over it every time. So,
Well, what program are you using?
Vim.
Vim?
Yeah, so if you go into
Yeah, Vim, you hit Escape, :WQ to right quit. All right, so now here's our build tool thing we just went through. And they show you this is what your directory structure should look like. So on our base directory, you should have our box resource file. We should also have kmain.c. We should also have a loader. This is kernel main. All programs begin and end with main. So this is where we're making our jump to our, I want my C code to be my main purpose of my operating system. This is kernel main. Make sense? Even though we have our loader in our assembly file for doing our couple of stupid things right now. Well, one required thing, setting up the stack, but then the stupid thing with the Cafe Babe, right? Just proving we can. All right, so directory structure should have that box resource file. It should then have a folder called ISO with all this stuff in it. It should then have kmain.c, it should have loader.s, and then it should have our make file that we just created.
Still have all my old crap in there as well. Hasn't been cleaned up
Yep.
at all.
So now we should be able to call upon the make program, which will look for a make file named exactly like that with a capital M. So notice when I call make, I'm not telling it about my make file. It specifically looks in the current directory for a file called make file that has all the right directives in it that make requires. So make in and of itself is like a language. All right. And I'm going to call upon that make file's directive called run. And what does run say do? Run says, we're going to build os.iso. What does os.iso say to do? It says, we need to build kernel.elf. What does kernel.elf say to do? It says, we're going to link these files. Then we'll be able to copy our kernel elf over. Then we'll be able to copy our ISO over. But before any of that happens, we need our .o files generated. And that's going to be our C compiler and our assembler. And in the end, if we want to call clean, we can clean it all up. And I'll show you that here in a second.
Oh, so
Yeah, see, it's complaining about syntax in that make file now. Did you mean tab instead of exactly 8 spaces? Great. Okay, number 12.
I think they did that for all of them. Oh, that's fun.
I look at the tab. I also look at the
Just
tab.
have it once for all of these.
Let's see if it's happier with that. Then we can just adjust it for all of them. All right, yeah, 15. So looks like this is.
This might take a while.
The rest of that stuff should be okay.
mine's giving it for line 12.
Well, I had it for line 12 first.
Yeah, that's the,
Oh, and then
that's the first one.
Then I fixed it. Then it's for 15. So now I'm fixing all of them.
And
So this is a cut and paste issue. So we cut and pasted it from the website. So think of make as kind of like a early rendition of kind of Python, and how Python has very specific indentation rules. So I haven't used make in years. This is all refresher for me as well. But make is great when you have it set up because it does all the heavy lifting for you, but you need to play make's game. You have to use its exact syntax with its exact spacing and all that jazz.
Why is it happy with the 4 spaces on all these?
All right, there we go. My emulator is now running. And I can come in here. I think I need to hit C. This was the thing that Luke and Austin didn't do. Remember me? I specified this, right? Don't forget to press C and press enter. I think I even put it in Slack. Everybody remember that?
The Slack channel.
You guys are idiots. On recording. All right, so I should have my Cafe Babe thing in here. So now if I say R for registers, there's my Cafe Babe. And look at this. Here's my stack pointer.
Nice.
Oh, wait, never mind.
So I have my stack pointer set to a real place now in memory.
Did you just run the make?
Yep. So here So notice here real quick, I have the O files and the loader files and all those out here. If I do make clean, it removed those for me.
Nice. Interesting. So
I'll go ahead and remove that a.out file here. So that's that. Now if I go in, just real quick, and I change my link LD, no, I'm sorry, not linked LD, my loader.s, and I no longer do this line, just let's just say cuz, yeah, I'll put a comment before it. So I do that, and then I come back out here, and then I do make run. Now it loads that guy. I still need to come into box and press C to continue, so it actually runs it. So if I come back out here now and I look at box, this is my grub output. So now I can safely kill it, do R. Oh, that's interesting. It creates a stack pointer on its own. So don't even pay attention to the stack pointer yet, because we're going to be using it with our code directly, but it does create one as part of a virtual machine. All right, so I'll put that guy back here. And if we want to just see that this stuff is still working, we can always move other things. So I can come in here and I can say move into EBX, the value 4 for no good reason. And I'll say make run. Did I write this? Oh, I misspelled move. All right, there we go. And that's my R.
I'd have to relook at the document.
And here's my 4 in BX. All right, that makes sense? All right, so now I can sit here and start making changes and just say make run or make clean, and it will run all my stuff. So I can quickly modify my operating system and get right back to testing it without all those manual things. But we do all understand each individual manual step, correct? We understand the value of Makefiles. Well, I mean, we did all the manual steps. Whether you understand the details, we spent a little bit more time today talking about the underlying details. What does a linker do? What does a compiler do?
Yeah.
What are those .o files? We talked about those individual pieces and how they play the larger game. Then what we wanted to get out of today is, okay, well, we proved that we can do it manually. But now if we want to do this often, and we could only imagine it's going to get more and more complex, more and more files involved, so we're going to have to update that make file as we get more stuff coming in here. So then at that point, what is the next step? So we're going to start putting stuff into that C file now
Okay.
to let the thing run, do something. Go ahead.
So with the make file, what exactly are we allowed to run? I mean, because we can do make run and make clean, but I mean like just based off of the file, trying to understand how it's structured. I mean, can we run kernel.elf also then?
Let me look at our file.
I'm just trying to make sure I understand what.
You can run the labels. So
Anything with a label like that.
yep.
So we could technically like do the %.o.
Yeah, you can run these individual things. So you could say make all, and that would make the kernel elf. And kernel elf is this guy. So that would not actually generate the ISO though.
Correct. Okay.
You could say make os.iso, which would then also call kernel elf.
Yeah.
So it would do those two things.
Yeah.
Make run does the three things.
So as far as making stuff in the future, if we need to have new labels or anything like that, can we have multiple make files, or is there only one make file?
You can only have one make file in a directory, otherwise
Okay.
make won't know what to call, but you can
Yeah.
have make files in other directories.
Okay.
And you can have a make file call another make file.
Okay.
But for us right now, I mean, we want to just appreciate the fact that, because what would happen before this? We could have created our own little script that did all our individual steps. So we didn't have to use a make file here. We could have just created a little text editor, a little text file, and put all those things that we did by hand. We could put those in there one line at a time,
Okay.
then change that file to an executable, and then do it. So I mean, in fact,
what would it look like to make that? Because I mean, like just seeing this is cool. This
sure. So it would be,
would it be like a bash script or something like that?
well, it would actually be, so these guys are, it would be a bash script, but you wouldn't need to even use bash language. Let me just look at our files we have in here. So we have kmain C, loader S, so we would need all of those individual things that we did beforehand for the O and the C files. So I'm going to keep my maker file open. So let me just create a new file. So I'm going to create a new file, and we'll save this guy. We're going to call this guy ghetto build.
Why is it ghetto?
Well, because you'll see.
There we go.
Okay.
So we're going to call this guy ghetto build. I'm going to copy stuff in from my make file. So we're going to have GCC with all these things after it. So GCC, all those things. Oh. And we're going to go down to our C file. So that's our C flags. And so we want to do this on all of our C files. And our C files we have out here is kmain.c. So we're going to do this to kmain.c. Then we have our linker stuff. So linker stuff says to do a LD link LD. Yeah, what was the I'm just going to scroll up. That'll be easier to get the values. So here is that line. Copying that. So there's my link. Then
Cool.
I'm going to do this file. Then I'm going to
We should do it all this way.
I'll do that.
So why doesn't it have to be in like a bash format? You mentioned that this isn't.
It's not. It doesn't have to be a big. You're going to see how I'm going to run it in a second.
Okay.
Alright.
So specifically the way that you.
So now I've generated the ISO. Now we need to move the ISO into the right directory. Oh, actually, no, we don't. Now we just run box. The ISO's already in the right directory. So there's box. That would be good enough. All right, so there's ghetto build. Ghetto build here says compile my C program, then link my loader to create my kernel elf, then copy kernel elf into the boot directory, then generate my ISO, then run box. So now I'll go back out here to the command line. If I do ls here, we see we have ghetto build.
Yeah.
I'm going to change the mode on ghetto build to be 755 ghetto build, so this will make it an executable. So it's executable, read, write, execute by owner, read and execute by everybody else. So now I could say /ghetto build, and it does the same thing there.
Yes.
And I can press C, and there's my thing. There's my cafe babe. Yeah. So if you really don't want to learn the,
Do it.
now you also you have to have a ghetto clean, a second file
Yeah.
called ghetto clean that will clean up all your.
Well, didn't you just clean it right after you run box?
Well, then you lost your ISO. Because one of the things
Oh,
it does
that's
is delete your ISO.
That's true. That's true.
In fact, it might yell at you because that guy's currently being used in memory. But let's just call it whatever. But so pick your poison. I mean, this is fine. I mean, so understand here that from a using Unix or using Linux perspective, if you just have, here's my 5 or 6 things that I want to do in a row, and rather than, I got them just right now, rather than have it, do it over and over and over and over again, I'm just going to put it into the script and do it. That's fine. A Makefile allows you to do that more with development in mind and in a more convenient way to add things into it once you have it initially working, with the trade-off of you have to learn the Makefile language. Make some sense? All right, so questions about any of the stuff we did today? Go ahead.
I missed a little bit with what's it called? Kmain.c.
Oh,
What are we using that with purpose right now, or is
nothing with purpose.
so it just needs to exist?
It actually doesn't even need to exist.
Oh, okay. Gotcha. Cool.
Yeah, it should exist so you have your starting point and your Makefile will work. But yeah, right now I have a function in here that I never call. And then I have a struct in there that I never use.
Okay. We're not going to use that function, but we're probably going to use something like.
Well, we will probably use that function as an example.
Okay.
But at this point, we've given ourselves our initial place for where do we start writing our C version of our operating system.
Mm-hmm.
All programs begin and end with main, or in our case here, Kmain. well, kmain's the name of the executable. Inside there, we'll have a main file. Yeah.
I'll just ask afterwards. I'll let you finish up.
No, I'm done.
Oh, okay. I'm getting error 13 invalid or unsupported executable format when I use make run. Do you know why?
No, I'd have to look at it a lot closer, but chances are it's, well, from what it sounds like to me is you didn't build your elf file correctly.
Probably.
So something that you did manually before, you're not doing automatically correctly now with the make file.
I see.
All right, so for next Monday, have all of this working correctly in your operating system. Pretty soon here, we're going to start deviating. Now we're getting into the C stuff where we can write our own stuff. We're going to start having some more specialized individual stuff. Make sense?
Yeah.
Questions, comments, concerns, bribes? All right, I will see everybody on, well, Monday.
How much
When
do
we
we have
get
to
the
bribe
belts.
you to stop putting stuff in Littman's drinks?
When you start taking his drinks.
Well, it doesn't require